from Southern Illinois University, Edwardsville, it's time for CMIS468, Business Telecommunications, with your host, Dr. Tim Jacks.
Okay, enough of that. There's your multimedia introduction. So welcome to our video catch-up lecture. This will get us back on track just to make up for the time we missed together on Martin Luther King Jr. Day. Here's our agenda. Talk about homework. I want to do a little review because we've been covering a lot of material at a fast rate so far, and I just need to wrap up domain name services in Chapter 1, and then we can jump into Chapter 2 together. So here we go. Please remember that homework number 2 is due on the 27th, next time we meet, due on Blackboard. Just submit it there. This is your packet capture, if I remember correctly. This is a very important homework assignment. These are mad skills that networking people use on a regular basis. You do want to finish up reading Chapter 2 before we talk about it in class together, just so you know what we're talking about, and you can ask some good questions about the material. Lots of tough material ahead, but useful, I think. And you do need to figure out what you're doing for your project by the 25th. Fill out the wiki that's on Blackboard and say, just put beside your name whether you're doing the individual certification project or a group project. And we'll go from there. You should, of course, remember the most important idea in networking, the layers, because we spent some time figuring out some very clever mnemonics together in class, so you'll want to remember what your mnemonic is when it comes time for the exam, as well as a certification exam. Remember the difference between encapsulation. Encapsulation is when the message goes inside the different folders like we did in class. That's encapsulation when you're going down the stack from layer 5 down to layer 1. In fact, encapsulation happens from layer 5 to 4, 4 to 3, 3 to 2, and then when it goes from 2 to 1, that's just, it's not technically encapsulation at this point, it's just converting the frame into a digital signal of in binary, zeros and ones. De-encapsulation is what happens on the other side when they receive that signal, converted into a frame, according to the syntax that we're going to talk about in Chapter 2. And then it goes back up the stack all the way up to layer 5. That's de-encapsulation. And the network application architecture, remember those are the three types that you need to remember. We talked about the difference between a physical link, a data link, and a route. Maybe another way to explain that is physical links are what connect one host to another. So kind of like the orange pieces of paper you guys were holding in the demonstration. Data link is the entire path from a host to another layer 2 device, like a switch, for example. And then a route is a path from one network to another. So within one network or between networks. Go back and look at those 3 slides that show you examples of the physical links, data links, and routes. And then the magic device that connects a LAN to a WAN, my favorite, should be your favorite device, a router or router, but we say router. Basically, the only protocol on the local area network side that we're going to talk about is TCP/IP, the TCP/IP suite of protocols. On the WAN side, there are a lot more protocols to worry about, but on the LAN side, it's pretty straightforward. We mentioned briefly how internet service providers talk to each other across NAPs. Those are network access points. Those are the routers where one ISP talks to another ISP. We started talking about DHCP versus DNS, but we need to cover that a little more in depth here right now. And then NAT, network address translation, serves an extremely important function, which we'll review here in a second. Before we dive into new stuff, I just want to review the most important thing again, the layers, because teaching is all about repetition. The more times you see this, the clearer you're going to get it in your head. So what I want to do is go ahead and watch the video that I skipped in class. We're going to watch it together now. If you've already watched this on your own time, great, excellent work, good for you. You can skip ahead just a little bit in this video, but we're going to watch it now. Okay, here we go.
My name's Phil, and in today's lesson we're going to talk about the OSI model and the 7 layers. The OSI model is broken down into the 7 layers so that it's easy teaching and learning, and also to break each individual layer down into different sections that cannot interact with each other or disturb each other's evolution. At the bottom of the OSI layer, you have what's known as the physical layer. This is classed as layer 1 of the OSI model. As we move up the OSI model, we've got layers 2, 3, 4, 5, 6, and 7. So if we label them up, there we go. As a user lives at layer 7, the application layer. So there's the user at the top end of the OSI model. This is because the user uses these applications, sits in front of a computer, and that's how they see the cells within this layer. On the left-hand side here, you can see the data units. These are also known as the protocol data units. Now, the protocol data units are how a packet of data is encapsulated as it's moving down the 7 layers of the OSI model. So as we're moving down 7 layers of the OSI model, this is called encapsulation. Okay, so there's your encapsulation. As the data travels across the physical media, across to the other side, to the other computer, it will then pass up the 7 layers of the OSI model, and this is called de-encapsulation. And it travels across there as a series of binary 1s and 0s across the physical link. This could be copper cabling, wireless media, fibre optic, radio waves, microwaves, whatever the medium might be. So on the physical layer, we've actually got media, signalling, and binary transmission of data. On the data link layer, we've actually got physical addressing, media access control. This is where MAC addresses live. And because of that, because MAC addresses live on the data link layer, this is where switches live. Okay, so therefore, switches actually forward frames which live on the data link layer of the OSI model. On the network layer, we've got logical addressing, or also known as IP addressing. Now, IP addressing happens at the network layer, and routers live at the network layer.
Routers?
So, we've got routers on the network layer, layer 3. We've got switches working on the data link layer, which is layer 2. MAC addresses on layer 2, which is what a switch uses to make a forwarding decision. IP addresses on layer 3, which is what a router uses to make routing decisions. Other devices on the 7 layers of the OSI model are hubs and repeaters. Now they're quite dumb devices, they live on the actual physical layer of the OSI model. These are just regenerating signals, so it's just boosting signal strength. The maximum cable run, don't forget, on an Ethernet network is 100 meters, so therefore the signal needs to be boosted. Back in the day, we would have had hubs and repeaters dotted around the network. Now you probably wouldn't see a hub or a repeater on an Ethernet network. It's more likely that you'll see switches, which are obviously a lot better at making decisions because you're actually looking at the MAC address and making a forwarding decision based on a physical address rather than forwarding all of the data to every device which is connected to the hub or the repeater. Also on layer 2, apart from switches, you might think of legacy devices as a bridge. A bridge just has 2 ports, one in, one out. It's just recording. It's a lesson. No matter. I was just testing. Alright. I'll stop now. I was just recording a lesson to put on Moodle. And I just wanted to see how good it was.
You got me on it,
yeah?
Yeah. Yeah, so obviously that was a student putting that together. It always makes me laugh when the guy barges in at the very end. I was just making a video for Moodle. So yeah, it's good to see this stuff several times, so it just makes it easier to memorize. Of course, he was showing you the 7 layers in the OSI model. We're just doing the simpler 5 layers in this class, but there are in fact 7. We can get into more detail in the future, but I just don't want you to be too confused by saying 7, because the top 3 just get merged here into one big, fat, chubby layer 5. Okay, on with the show. We started talking about the supervisory protocols. We got into DHCP is what gives you an IP address when you boot your PC, specifically when the operating system loads is when you're going to get your IP address. The DHCP server actually gives you a lot more than just an IP address. It actually gives you five pieces of information. We'll talk about the 5 later, but it does include your default router, i.e. your closest router, as well as the IP address of your DNS server. So that's important. Network address translation. If you're familiar with this already, it's straightforward. If you're new to network address translation, sometimes it takes several reviews to get it. So there are 2 big reasons why NAT is important. One is to give you more IP addresses. We have a limited number of IP version 4 addresses. In fact, there are none available on the public network, i.e. on the internet. There are no more available, which is why we're switching over to IPv6 version 6 that we'll talk about in class together. But NAT is the protocol that allows you to have more devices on your home network than just one. The second thing it gets you is security. So if you were publishing your actual IP addresses, your real IP addresses, outside your firewall, well, that's a safety concern. It's a security issue because if I know your IP address, I can launch all kinds of attacks on you. But if you're hiding behind a firewall that's doing network address translation, it's one more layer that I have to get through to get to you. So it's more IP addresses, better security. And so now we get into some new stuff with DNS, domain name, the domain name system, and domain name services. DNS is another great example of a client-server networked application architecture. It's one of the big 3. So DNS, there's a client request, and a server has to respond to that request. So in our example here, the host wants to go to voyager.chidler.hawaii.edu. I think this is the university where the author is currently teaching, and there's an IP address for this host. And the question is, how does the host know that this is my DNS server? How does it know where to send the request? Interesting. You already know the answer, because we did mention it already. Yeah. Let's back up a second. Let's go back here. When DHCP assigns you an IP address, it gives you the address of your router as well as the IP address of your closest DNS server. So that's how it knows how to make this initial connection. Yeah, important stuff. Good stuff. Okay, step 2. Step 2 is just trying to do a lookup to convert a name to an IP address. So exactly like a telephone book. Sorry. Telephone books were things we had back in the olden days. It was like a book with pages in it, and you could look up somebody's name alphabetically and find out what their phone number was, in addition to their address. And DNS works in a very similar way, so computers and routers understand IP addresses. The only reason we have DNS, the only reason we have names, is because it's easier for human beings to remember names than numbers. Therefore, that's why we use DNS. That's the only reason we even need it. So step 2 is the lookup. Step 3, that closest DNS, we'll call it the local DNS server, responds, oh yes, I know where Voyager is. Let me send that IP address. It's 128. Whatever. So it sends it back to you. Once your PC, laptop, tablet, whatever, has resolved the name to an IP address, it doesn't have to keep talking to the DNS server. It just does that once. Once it has it, it goes directly to the server and it can begin communicating with it because it's actually stored locally in its cache, specifically in its ARP table, which we'll talk about. We're going to talk a lot more about DHCP and DNS in a future chapter, but right now you just need to get it clear in your mind the basic difference between the two. The DHCP deals with IP addresses, DNS deals with names, and remember every host on the internet has to have a unique IP address. Now students get DHCP and DNS backwards all the time, I guess because they both start with the letter D. And actually, typically, both DHCP and DNS are running on the same server on your network. So they're both kind of lightweight services running on a server that you would rarely ever have a dedicated DHCP server or a dedicated DNS server. Usually a server is doing double duty. Typically, it's your Active Directory box that's serving up DHCP and DNS. Is a typical setup for an organization. So DHCP sends you the IP address of you, right, your IP address. DNS sends you the IP address of where you want to go. So if you want to think of this as you, here and there, or you and somebody else, or your IP address and the IP address of the name to which you want to go. Again, just something you have to memorize. These are things that are very changeable. So on the client side, these are old screenshots from like Windows XP, so bear with me. But actually, even if you open it up in Windows 10, it looks about the same. Notice that here, right here, if you look in the properties of your network card, you can see Internet Protocol TCP/IP. This is the software. This is where TCP/IP is installed. If you don't have this protocol installed in Windows or Mac or Linux, it's not going to be able to communicate. So this is installed by default, and the default over here is to obtain an IP address automatically. They did not say enable DHCP just because they thought that would confuse end users with another acronym. So they tried to make it a little more friendly to say obtain an IP address automatically. But that just means it's using the DHCP client. If you want, you can turn it off by clicking the other radio button and assigning yourself an IP address here. And in fact, you can assign yourself a different DNS server. Be careful with this because it's very easy to disconnect yourself from the network if you don't get it exactly right. You have to make sure you're using an IP address that's not used anywhere else. You have to make sure you're using exactly the right subnet mask for your network. More on that later. And make sure you're using the right default gateway. If any one of these numbers is off by 1, doesn't work at all. And on the server side, if you're wondering what a DHCP server looks like, it's just another service running. There's a configuration tool you can launch, DHCP Manager. If you're wondering how the server knows which IP addresses to hand out, this is how. The person who decides is you, the network administrator. So you assign a range of addresses to hand out. It's called a scope instead of a range. And you give it a lease time. We'll talk about the lease time later, but how long the IP address will be good for. You can set that up. You set it and forget it. Normally, you never have to go back here and fiddle with it. And similarly, there's a DNS Manager utility where you can kind of change some parameters around how domain name systems works. But again, once that's set up correctly, there's no need to go in and make many changes. Unless somebody wants like a DNS shortcut, an alias, something like that. Please notice from the first homework assignment that you can ping either an IP address or name. You can ping space www.google.com, or you can ping an IP address like ping space 192.168.111.1. There are some devices on the network that you do want to be static. So you might think, well, if DHCP just takes care of IP addressing, why don't we enable that for every device? That's fine for PCs, laptops, tablets, and such, for end users. It's not good for the equipment that you're going to be supporting. You definitely want to assign a static IP address for all of your router interfaces, for all of your access points, typically for your printers, and definitely for all your servers. You just don't want your servers wandering around the network and you're not sure what IP address is assigned to them and you have trouble finding them. That's why you want them to be fixed. So there are pros and cons either way, but you don't want to statically assign everything just because there's an administrative overhead to that. You have to track everything, typically just in an Excel spreadsheet, although there is software that can track this for you as well. Some businesses are moving towards this, statically assigning every single IP address, just because DHCP can be a security hole. If you think about it, a vendor, anybody, a guest can walk in off the street, plug into your network, just plug in with an Ethernet cable, and immediately get a valid IP address if they have DHCP turned on the server and client end. So some people are turning it off, but really it just saves so much time and energy. People do half and half. They'll turn on DHCP for all of their client machines, but they'll use static IP addressing for the network and server equipment. So in a nutshell, these are both databases. There's a DHCP database, a DNS database on the back end of that interface I showed you. It's a database that resolves MAC addresses, so the MAC address on your network card to an IP address. And the DNS server is a database matching IP addresses to domain names. So MAC addresses to IP addresses to domain names, and they're typically run on an AD box, or if you're in a Linux environment, an LDAP box.